Okay. This model you see in SolidWorks is it's a model of a link. Just pay attention on how it moves, because we are going to use this information on the nodes in a few seconds. So I have a link, I have a joint, and this link is allowed to move this way only. So you can start guessing which type of position vector I will need to represent this link. Okay, this is one case. Let me show you another case. I have another case of link. Is inclined, and this is the movement that is allowed in this system. Okay, only linear movement. You can guess which type of vector, position vector, we should use to represent this one. Okay, second example. Let me jump to a third one. Look at this one. Look at the movements that are allowed in this system. So this can rotate, but the slider can move also. Okay, so you can think on which type of vector I'll need to represent the position of this one. Okay, let's see all of them again, one last time. Let's go to the first one. Type of movement allowed. Second one. Type of movement allowed. And finally, whoops. Type of movement allowed. Got it? Okay.
Profe, the last one is just oscillating.
It can have a full rotation, but I didn't do that because it's Monday, but it can have a full rotation.
Okay.
Okay. Okay. Let's draw the first one. Oh, I can have it from here because I did a screenshot. That's the first one, if you remember. Yeah. That's the first one. Okay. I'll fix this here. And I'll do a kinematic diagram to represent this system. So my kinematic diagram would be do you agree? That diagram is a simplification of what we are looking in the model, in the computational model. And I need to propose a vector. Yeah, I need to propose a mathematical way of representing this system or this link. And for that, I propose the following vector. And you know that that vector needs a magnitude and orientation, basic position stuff. So which type of position vector is this one?
Constant variable.
Constant variable. Okay. Constant variable. That's right. Don't know who said that, but he's right. And then, can any of you tell me what this vector is equal to? Having the magnitude and the orientation, tell me what this position vector is equal to.
Do you mean the equation?
Yes.
It's r angular velocity.
Why angular velocity? We're talking about position.
Ah, okay, yes. Well, then you got it. Cosine cosine.
Life is normally simpler than you think. So that's the position vector, right? I need the magnitude and I need the orientation. Okay? Easy stuff. Let's analyze the second one. Let me grab the second one. Okay, this is the second type. I'll reduce a little bit the size. And again, I need to draw a kinematic diagram to represent whatever I'm looking at from the model. So tell me if this diagram is accurate or is complete or is good enough. You think is that correct? And if not, what am I missing? Let me ask.
Fixed basis.
Spaces, say that again.
The fixed basis.
Oh, the fix. Okay. You think that adding these lines is enough to say that that link is fixed? That the axis in which this slider is allowed to move is fixed? Yeah? Of course, you can also do the other proposal, which I think is what Mauricio was trying to say. The one with some fixed elements here and the slider in the middle. That's the one you said, right, Mauricio? Yeah. Okay.
Yeah.
Well, this bit is kinematically equivalent to that one. I'm just trying to show you a different way of representing it, but you are right, Mauricio. I need something to tell whoever is trying to read this that the axis in which the slider is moving is fixed. Okay. Now I need to propose again a vector to mathematically represent whatever I'm looking at here. So the vector will be that one. And for that vector, I need a magnitude and I need an orientation. Given that magnitude and that orientation, tell me the equation or the mathematical expression for the position vector for this case, Fer Alonso.
It's the same.
Is the same. How boring it is, right? So cosine, oops, I forgot the orientation. Cosine and sine. Magnitude and orientation. Easy stuff. Let's do the last case. Last case, let me grab the figure from the SolidWorks model. This is the last case. I fix this here. And again, let's draw a kinematic representation of this thing. Okay, that's the one. What am I missing, Pablo Candelas? Let me improve the line.
Only one fixed base.
I need to say that this joint here is connected to ground. Like that, right? And again, let me represent a vector. Let me propose a vector to mathematically represent this thing, which is going to be that. I need the orientation and I need the magnitude. And again, Fer Alonso, which is the position expression for this vector that is representing this system here?
I think again it's the same.
You see how ship I am? Super barco. Misma respuesta para diferentes preguntas. Easy stuff. Okay. This was a constant variable. What about the second one, Aaron? What about this one?
It's also a variable. Ah, no, the second one
The second one
is a constant orientation, a variable
variable magnitude.
variable
constant
magnitude, constant orientation. Yeah.
Okay. Majo, what about the last one? Which type of vector it is?
Both variable, magnitude and orientation.
Variable. Sweet. Let's carry on. Now velocity, Fer Alonso. I hope you're ready because the answers are going to be different to each question now. Let's start with the velocity for the first case. Now, keep in mind something. The stuff that is changing with respect to time, in this case, the orientation is changing with respect to time. That is going to produce a certain type of velocity. If the orientation is the one that is changing with respect to time, then I will have a change in orientation with respect to time, which means an angular velocity, right? So, tell me the expression of the vector for velocity for a case in which I have constant magnitude, variable orientation. Fer Alonso.
That would be R then
Magnitude,
times angular, well, magnitude times angular velocity.
which is
You
omega.
open parentheses minus sine omega I plus
Theta.
cos theta. Yes, I don't know why I said omega. Theta and J.
Okay, so that's my velocity vector. Okay. I'll give some space because I think for the last one I'll need more. Okay, that's right. And all of us should remember where this omega comes from. If you don't, check the video for the velocity topic and you'll remember where the omega comes from. But just as a hint, as a reminder, you know omega is the change of angle with respect to time. Okay. Now, let me ask someone else. Fabiola Zapata, can you tell me which is the velocity vector for the second case, when the magnitude is variable and the orientation is constant?
I don't have my notes here, but I kind of remembered it was magnitude.
I think it's not that hard because if you see, the orientation is not changing. So that bit has to remain the same. So I can go ahead and write the orientation the same as in the position. And the only thing that is changing is the magnitude. And you know that when the magnitude is changing, you have a linear velocity. Because this linear velocity is the change of magnitude with respect to time. Okay?
Oh, yeah, yep.
Now, Maritza. Si es que estás con
Yes.
nosotros, yeah, tell me the velocity for the last one.
It's linear velocity times cosine theta plus sine theta, cosine theta I sine theta j, plus the position, the r,
Magnitude,
At times angular velocity and minus sine theta I plus cosine theta j.
J. Okay, easy stuff. That's the velocity. That is the velocity, which up to this point, it is a combination of the first case and the second case. Okay, let's carry on. Because peeps, get ready, because things are going to start getting dense. Because the next column here is acceleration. Now for the acceleration, I need to derive all this with respect to time, right? So let me write that down again here. From these three things, which are the things that can change with respect to time for this case, where the magnitude is constant and the orientation is changing? So which of these three things, which is nothing but exactly the same as the velocity vector? What about the omega? Can it change with respect to time?
Yes.
It can.
Yes.
It can. Can the orientation change with respect to time? Of course it is changing. It is rotating, but the magnitude is not. So when you derive this with respect to time, you derive only this bit. Okay, let's derive that, because here you have another derivation of a product. So I need to derive the first one, keep everything the same, then derive the second one and keep everything the same. So when I derive the first one, I end up having magnitude, the change of omega with respect to time, and everything else stays the same, which is minus sine plus the cosine. And plus, I keep everything, I keep the first one as it is. So I'll have r omega. And I derive whatever is inside the parentheses here. I need to derive that. So when you derive minus sine of theta, what do you get?
Minus
Minus
cosine.
Minus
cosine.
cosine.
Minus cosine. So I get minus cosine of theta times the change of theta with respect to time, because that bit is changing with respect to time. What happens when you derive cosine? What do I get?
Minus sine.
I get the minus sine of theta times the change of theta with respect to time. That is in J. Now, a few things to know here is that this bit here, you know what it is. What is this bit? The change of theta with respect to time.
Omega.
That's
Omega.
omega. And I also have an omega here. So the second term will end up being r omega squared minus cosine of theta minus sine of theta. Okay. What do you think is the change of omega with respect to time?
Alpha.
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 That is the angular acceleration, which is alpha. So the first term is r alpha minus sine plus cosine. All this here is the acceleration vector when the magnitude is constant and the orientation is changing. Okay? The first bit is known as tangential acceleration. And the second part is known as radial or centripetal. All this bit is the acceleration vector when I have these kind of links. Okay? Preguntas? Any questions? Nothing? Easy stuff? Miguel Ángel? Fer Terrazas? All good? ¿Sí? Gustavo? ¿Todo bien? Okay, let's carry on. Now I need to derive this one with respect to time. If I derive that with respect to time, the only thing that is changing is this bit. So it will be that with respect to time times the same orientation. So in the exam, I can ask for which type of position vector will the acceleration vector have the same orientation. You know that can only happen when the orientation is not changing. So for a position vector for variable magnitude, constant orientation. You know what this bit is here? This one here, what it is? What is it? Say that again?
Velocity.
No, this is velocity with respect to time. So it is
Acceleration.
linear acceleration. So the acceleration vector in this case will be simply linear acceleration times whatever the orientation is. This bit here is the acceleration vector for the case in which I have variable magnitude, constant orientation. I end up having the following acceleration vector. Okay? Get ready because the following derivative is going to take us up to 10 a.m. A las 10 vamos a acabar de la siguiente derivada. Que se pongan cómodos.
But we just have to ask the other two, no?
No. You'll see in a second, Salvador. You'll see in a second. Let me get ready. Okay, let's do it. I'll write exactly as it is the velocity vector. So I have the component that has the angular velocity minus sine plus the cosine. Okay, and I'll write the one that has the linear velocity, cosine and sine. Now, this bit is changing, that bit is changing, that bit is changing, this bit is changing, and that bit is changing. So you cannot take out anything from the derivative. So let's go step by step. In the first case, I need to derive the first one, keep everything the same. Then derive the second one, keep everything the same. Then derive the third one, keep everything the same. And in the second one, derive this one, keep everything the same. Then derive this one, keep this one the same. So step by step, slowly, breathe. Sale, Gustavo, respira profundo. It's going to take a while, but I think once we get it, you are ready for the second partial. Only if you know how to apply it. Okay, so I'll derive the first bit. So if I derive the first bit, it is that times omega times minus sine, cosine, and that's it. Now I'm going to derive the second bit. I'm working only on the first term, okay? So when deriving the second one, I have r, the change of omega with respect to time, and the same orientation still. Now I derive the third one. So I have r, omega. And what do I get when I derive the third one? Which is the derivative of minus sine? It was minus cosine, right? Minus cosine of theta and the change of theta with respect to time. Okay. And then what do I have when I derive cosine? I have minus sine. All these three terms, they only come from deriving the first one. Okay. Let's derive the second one. The second one would be, I derive the first one and I keep everything else the same. I keep the first one the same and derive the second one, which is going to be minus sine. You know, every time I derive the trigonometric function, because the angle is changing, I need to include the change of that with respect to time. And then I derive sine, which is going to be cosine. Okay. Let's simplify then. Let's see, what do I get in the first one? What is this? What is this bit?
Linear velocity.
Linear velocity. Okay, so let's not forget that this becomes linear velocity. Okay, so I'll have linear velocity omega minus sine times the cosine. What do I get in the second one? You know that this bit is what, Pablo Candelas? What is this bit?
Alpha?
That's alpha, angular acceleration. So for the second term, I have this. Okay. What is this bit here, peeps?
Omega.
That's omega. So this second term will be omega squared minus cosine minus sine. Okay. What do I get in this part? What is that?
Linear acceleration.
Linear acceleration. So I'll get, oops. Linear acceleration, same orientation. What do I get from the last bit? You know, this becomes omega, right? So I'll end up having linear velocity omega minus sine plus the cosine, and that's it. All this bit pips, all this is the acceleration vector when both of them are changing. Magnitude and orientation. Now, I wasn't recording. Let's do this again. Nah, I was joking, I'm joking. Vi la cara de Pablo y dijo, no, no puede ser posible. There are some terms that are common. You see, I have this linear velocity omega with minus sine and cosine 2 times, you see? So those two can get together. Let's simplify them. I'll simplify. So I end up having r omega squared minus cosine plus sine. No, this should be minus, sorry. Minus sine. Okay. I have that bit minus sine plus cosine. Okay. I have that bit a, sorry, linear acceleration, cosine, sine, and finally I have 2 times linear velocity, angular velocity minus sine plus cosine. All this is the acceleration vector when both of them are changing. So Salvador, you see, it's not simply summing everything else, because if you sum everything else, you end up having only that bit, that one, and that one. You are missing this term, which is very important. I'll tell you why. This first term, yeah, this one here is the radial acceleration. You remember, we write it here, radial. So this is the centripetal or radial. This bit here is the tangential. This bit here is the linear acceleration. And this last term is called Coriolis acceleration. So the Coriolis acceleration only appears when I have an object that is not only moving linearly, but it is also rotating. If you remember where it comes from this system. Yeah, when the slider was allowed to move linearly at the same time that it's rotating. When you have that combination of movements and you follow the procedure, you end up having the Coriolis component or the Coriolis acceleration. Okay. Okay. You know that you can propose a vector to solve this one, a vector loop equation. That vector loop equation consists of 3 vectors, if you remember. Let me draw the vector loop equation. I propose that one to go like that. I don't know if you managed to see those colors. If you want, I can change colors. Remember that I don't even see any color at all. So I think that one is more evident, right? See, vector razas, no? Okay.
What color do you see on that one?
You see an arrow. I don't worry about which color it is.
Okay.
And then that's the second vector I propose. And finally, this one here. Yeah. So these I'll label it as R1. This is going to be R2 and R3. So the vector of the equation is R1 vector plus R2 vector plus equal to R3 vector. And I know which type of vector is this? R1.
Constant.
Constant. What type of vector is R2?
Constant variable.
What type of vector is R3?
Variable.
So this one here is not going to participate in velocity and is not going to participate in acceleration. But this one here results in which type of vector, at least for velocity. So let's say velocity vector V2 would be which type according to this table?
The second one.
Second one? I don't know if we have any of the second one in this mechanism because we did say that it was constant magnitude, variable
Like
orientation.
the first one.
It has to be the first one, okay. What about this one? The last one, right? Variable will be this velocity vector here. Okay. And when you, so let me complete the notes. This is the first one, and this is the third one. You know what these numbers will mean. ¿Sí? Ustedes saben qué significan estos números. If I derive this with respect to time and this with respect to time, which type of acceleration vectors I have? Of course, you know, this is the first one and this is the third one. So in the first one, you'll have angular acceleration. And in the last one, you'll have angular acceleration, linear acceleration, and the Coriolis. So this vector here will be this type, this very long one. Okay. Let me show you another example, just for the fans. Uno se debe a sus fans, entonces, pues ahí les va otro. See if you can get it. It's always for the fans, right, Miguel Angel? We do everything for them, always for the fans. That's the one. Do you think I'll have a Coriolis component in the analysis, in the acceleration analysis of this mechanism? Coriolis component or not? Okay, yes. Why? Can you draw on the screen and show us why do we expect a Coriolis component in the acceleration analysis of this thing?
I don't know how to draw.
Oh, that's a
Okay.
perfect arrow. How do you get a perfect arrow? Might be too late to ask. Llevo todo el semestre haciendo flechas y hasta ahorita supe que se podían hacer perfectas.
Ahí salen aumentar, profe.
Oh, sorry, let me try.
En el de dibujar salen las flechas.
But I think it would move when you move the screen.
No, in dibujar.
Oh, arrows, wow. Jesus, no way. Okay, we know that I can draw arrows now perfectly. I'm sorry, didn't know that. Didn't know that, sorry. Let's clear everything. Now, Gustavo, please explain again, sorry, which is the bit that gives us the Coriolis component.
This one.
Okay, so that vector that you are drawing there is allowed to rotate, so its orientation is changing, and it is used to represent the magnitude of how far this slider gets from this point. So the magnitude is also changing. This type of vector that Gustavo just drew is a variable. And once you have a variable in your vector loop equation, you know you'll have to use, oops. You know you'll have to use, I'll get rid of the drawings in a second, this type of vector. Okay, the very long one. Thank you, Gustavo, for erasing, or whoever did that. Right, so you saw two examples in which the Coriolis component will appear.